As in previous section, we have discussed about kinetic and potential energy of a particle. Let's discuss the variation curves of these energies. As we know, we have just now studied that potential energy as a function of y can be written as half m omega square y square, and if at mean position potential energy is taken to be 0. Under this condition, the potential energy at a general displacement can be given as half m omega square y square, and kinetic energy as a displacement function can be given as half m omega square a square minus y square. So here if we carefully observe the two situations, we can state that potential and kinetic energy both depends on second order of displacement. So when we plot the curve, it will be a parabolic curve, and if we just draw the curve with potential energy or energy as a function of displacement, then potential energy curve can be simply drawn like this. It will be a parabolic curve where we can state at extreme positions at y equals to minus a and y equals to plus a, the energy can be given as half m omega square a square, that is the total energy. So this straight line can also be written as the curve of total energy which remains constant. Now if we draw the kinetic energy variation with displacement, we know that at mean position kinetic energy is equal to total energy, and at extreme position it is 0. So this curve will look like this. Here we can state this is the curve for potential energy, which is half m omega square y square, and this is the curve of kinetic energy as displacement function, which is half m omega square a square minus y square. So be careful about both of these curves at any general position y. If we just calculate the kinetic energy, potential energy, sum of these two will always be equal to total energy. Now in the previous situation, we have taken potential energy at mean position to be 0. Now if at y equal to 0, that is at mean position, we take potential energy to be equals to u naught, which is the minimum potential energy in the particle when it is at mean position, then we can say that potential energy as displacement function will be u naught plus half m omega square y square, and kinetic energy as a displacement function will remain same. It is half m omega square a square minus y square. And in this situation, obviously, when we just add the two, total energy of the particle can be written as u naught plus half m omega square a square. We already studied these terms in the previous section. Now if we plot the variation curve of energy with the displacement, here we can state the kinetic energy as expression is same, its curve will also remain same, that at extreme position you can say that kinetic energy will be 0, and at mean position kinetic energy will be half m omega square a square, and at y equals to minus a and y equals to plus a, at both the extremes kinetic energy is 0. So this is the curve for kinetic energy. If we plot the curve for potential energy, then we can state at y equals to 0, that is at mean position potential energy will be equals to u naught. So the curve will be slightly changed. It will be raised up by a height u naught, and you can say the curve will now look like this. In this situation, at extreme position, the total energy will be potential energy, and there is the line for total energy, which is u naught plus half m omega square a square, and at a general position there is the curve for potential energy as a function of displacement given by these expressions.